Okay, I think we're back on track, people. So I'll be using this image. So to load this one, you can run like this piece of code. So let me just provide it in the on Slack as well. If people want to follow along with this one, although if you can load whichever image you want, but yeah, let's move on with this one. It's also kind of smaller, so
No, just copy.
oh yeah, sure. Still, I don't have that, but I'll do the conversion, I guess. Yeah, let's start. Let's go from here. Okay, histograms. Oh, yeah, I guess I can take it. Okay, I guess you're getting also a sense of how different images vary in their histograms. And in fact, people used to use the color histograms to do also classification. So they would use the frequency of each color in an image as a feature for that specific image. And because it's obviously much more lower dimensional compared to the original image. So for the images that I'm using, for the flower image, for example, if you see here, it's 2000 by 3000 by 3, which means that overall it's like 10 million values. The color histogram is expected to be like a lot sparser, say, or much more lower dimensional. A worst case, if you take every value for every color, you're going to have 255 by 3. So that's around 1000, say, and therefore it's 3-4 orders of magnitude smaller representation for the image compared to the original data. So when there's not a lot of compute, or when you don't have strong algorithms to extract features, which we now have, you can just use the values of the color histogram to perform classification. And also you can take regions of the image and extract color histograms for those, and then concatenate and use that to perform like as a representation for your image to do downstream tasks like classification. So let's see, I hope this works. Yes. So again, after performing equalization, now it may not be useful in itself for a single image, but if you are talking about an algorithm that has to learn from multiple images, then having like uniform ranges across all your images in your training set or in the evaluation set is going to be beneficial, because there's not going to be a distribution shift, say, from training in a certain brightness range to then going in another setting where your algorithm has to perform without training and seeing other distributions in brightness. So if you kind of make them more uniform, then you can at least ensure some generalization to unseen images. Let's run the thresholding for the cuts. Yeah, and just the inversion. Okay, we also talked about this, but let me see if I can actually run the interactive stuff. Yeah, okay, you can see into that. Let's not try not trolling as well. So why would a transformation like translating the image be useful? Is, well, it's more so used when you're doing cropping, but say you have set up a task where you are either trying to classify what you're seeing in this image, or you're trying to count the number of cats in the image. So you want to build a model that's able to either distinguish between cats or not cats, or cats and other animals, or you're doing counting or whatever. You'll notice that both images or like would retain their labels, their ground truth labels. So you can see cats in the translated image as well, and you can see two of them also. However, the pixel values are significantly different because, the way, you are able to obviously perceive it as being the same, but for a computer, you're going to have a huge shift in values. So the values between, if you take corresponding values from the left image and the right image, you're going to see that they're all different, except from that part, which I guess the translation retains in that specific implementation. So this is a way, for example, to give an algorithm the knowledge that, I want you to be looking for concepts all throughout the image and not in a specific place. And there are other mechanisms we can leverage. For example, we have flipping. So again, two cats are present in an image. The semantics of the image don't change, but the pixel values in the image are going to be very different compared to the original one. And that's why we are also doing rotations. You need to be careful with rotations depending on what task you're doing, as well as with flipping. So for example, for flipping, if you're trying to classify, say, digits or letters, then flipping would actually alter the digit that you're looking at. So it's going to change the semantics. So think of like, in the case of rotation, I guess it would make more sense. Think that on the left, you have a 9, the digit 9. If you rotate it enough, it's going to start looking like a 6. But if your label stays the same, which in your data is going to be the 9, then that's going to actually alter the semantics and perhaps going to confuse the algorithm. So these are very useful techniques to create extra data, which we call data augmentation. So the image on the right is obviously very different than the image on the left in terms of the individual pixel values and especially corresponding pixel values again, but the semantics are relatively the same. And I guess safer techniques can be resizing. If your algorithm is able to handle images of different sizes, then maybe that's also going to be of use to you. And finally, something that you'll also have to apply with a lot of care is image cropping. So you can see if you crop a very small region of the image, then you're actually not getting anything at the result. But let me increase. The size a little bit, it's not doing too much. Yeah, we're starting to get some random pose there. We're starting to get the body of the cat. So it's kind of clearer. So the bigger your crop is, the more of the semantics of the original image are going to be retained. So yeah, here, for example, you may be able to say to an algorithm, I have on the left an image of a cat, but on the right, it's also an image of a cat. And again, you can see how different this is. And when you're doing cropping, the other information you're adding to the knowledge you are exposing the algorithm to is that objects can appear at different scales. So you can see on the image on the right, the cat is much bigger than it is on the image on the left. And that can be very useful knowledge if you just want to do like cat classification. Cats can be on the background, can be on the foreground, can be they can be in the entire image, can be on the top right. So these are properties of images in terms of their high-level semantics that we humans are very easily able to perceive. But for a computer algorithm, it's going to be useful to use these data augmentation techniques to create this extra data that contains this information by virtue of transforming the pixel space, trying to retain the high-level semantics of I have cats sitting on a bed, and therefore keeping the label the same. And you can also, yes, play with a little bit of the brightness. So why would a transformation like that be useful, and where? Can anybody take a guess? Like what properties of the high-level semantics does that represent, given that we'll keep the same label of there is a cat in the image for the computer? No guesses? So I guess one idea is that you may be using different lenses to take the pictures, and you want to try to simulate that effect by changing the brightness. You can see maybe on the right, that could have been an image from a camera, like a 40-year-old camera or something like that. So this is something else you can leverage in your like data augmentation techniques to, again, you're giving extra information to the algorithm without actually going through the trouble of going and collecting data. So for example, if you wanted to get this effect in your algorithm without data augmentation, you would need to take like the same pictures or different pictures with different camera lenses. However, now you can just use the same camera lens and then applying the filtering afterwards and get this effect very cheaply. And do you want to do the FFmpeg?
So another tool that we have in our arsenal is FFmpeg. This is supposed to be a picture here. It was just a picture of a kineograph, which is like, you know, those books that you flip to see the objects moving. Oh yeah. So this is a like very basic idea that has followed us like to this day. You know, a video is nothing but a collection of images that you see one after the other, and each image in that is called a frame. So when we talk about frame per second, it's like how many frames are you flipping through in the video per second. So a little bit about the video formats that are available. We obviously know the most popular ones, MKV, MP4, MOV, and then some other that are not as popular, you know, SLV, AVI. I don't even know this one. I don't think anyone actually uses that. Probably just like Sony people.
Some of them may be used for scientific purposes also.
Oh,
like for images, TIFFT. I think I've used it only in applications where we're dealing with very remote sensitive data. So like photographs from satellites. So
yeah. And then some other terminology that is associated with videos is the aspect ratio, where it's the ratio of the width to height. Codec, which is how that video is actually encoded and how it is stored in your system. For example, H.264 is the most widely used codec. And then the container is your container like MP4 MKV, which has the the data as well as some metadata, like the title, resolution, etc.
You can double click on the cell. You actually have to press the track button.
I've never used a Mac.
It wasn't too informative, but
all right, so this is a library from Python, ipython.display, which you can use to embed like videos and sorry, not videos. You can use it to embed HTML in your Python notebooks. So this is the HTML element that you can use to do so. And then inside, we're just writing HTML to display that video. So this works. Why does your left click not work? Okay.
left click might be you need to
Yeah, I got it.
press two of them maybe. Two fingers.
I am trying to run it again because it's not playing.
Yeah, anyway, notebooks sometimes can be a very tricky business. There are a lot of utilities you can use in like normal terminals to run Python that
Okay.
do not work for notebooks. Like I showed you PQTM in the workshop last week, where we were getting those bars to show the progression during training. Some of these utilities might not be working for notebooks, but only for your terminal. So TQDM works for notebooks, but I've run into like other similar utilities that just give you sort of like an HTML code instead of giving you the actual output. I guess that's one of the things that can happen. It can depend on the browser. It can depend on a lot of stuff. So.
You guys can try to run the notebook in your own laptop. Maybe it's the Wi-Fi that's not working because it's a video that's taking from Google Drive. So that might also be a reason. Right? It's just a movie clip. It's nothing like too complicated. So we can use some JavaScript to play this back at like a 2.2 rate. And then also we can like slow it down. So the speed that you select for the video translates into the FPS that you're selecting. How many frames are going by per second. Okay, so onto FFmpeg, you need to install it. And then these are the commands that you generally use. So you specify the global options. So for example, one global option that you might use is -y, which is like you need to overwrite. So whatever transformation that you're doing through the command, you need to overwrite the output files that are generated. You can specify input file options, the name, and then output file options, and the name. So look at this command right here. -y, that means that this command needs to overwrite output files if a file of that name already exists. You're specifying the input file name here. So we're taking this file, and then you're specifying the audio codec and the video codec. So videos are basically, so how images are like 3 channels, videos are made up of 2 channels, the audio channel and the video channel. So right here, you're specifying what is the audio channel for the input file, and then the video channel for the input file. What are the codecs that they're using? And you can use the other options, the output options, to specify the the codecs for the output file. So this shows. So while it's downloading, you can use ffprobe to find out the metadata for the video, which you can see right here. Yeah, see, it's the information about the audio and the information for the video stream. So you can also use FFmpeg to convert like formats. Finish. So right here, we're just converting between MP4 and MKV. So this is just to give you an example how to use these commands. You can also use it to clip your video. So for example, if you're like trying to create a tool, like a video editor or something, you would use FFmpeg because it is the most popular and most reliable. Let's see if it plays. So this is the video that we made faster and then we clipped it. So, that's all fine, but then how do you do it using OpenCV? Like what tools do you have for doing that? So you can use OpenCV to get information about the image. So you have this video capture object. You can, like use these get methods to get the width, height, the file per second, the size. And this right here, what we're trying to do is, pick out a specific frames using this cap.read method. And then we are trying to make it gray. Yeah, right here, we're trying to make it gray, and then we're flipping the video. So like flipping the frame so that the entire video becomes flipped. So another thing that you need to be mindful of is that like video processing will take a lot of memory. So you want to, like how in C you release pointers so that you can, clear up your memory. You need to use this method destroy destroy all windows to clean up objects. So that's the cleanup part right here, where you're doing like releasing the memory that is held by those objects. Yeah, this image is just converting it from MP4 to it's like doing the encoding so that we can display it. Where is the display? It's right here. For another minute. See, it's all in gray, and because we use that BGR to gray, and then it's flipped. So you're basically, like decomposing the video into frames and then acting on those frames and then creating a new video from that. And that's the end of the video processing. Do we have anything else to come?
I think we can go through the torch vision transformation track.
Do you have my number?
It's the one that added yesterday, right? No, let's do it now because next time we're gonna look at models. So we showed you how you can do all these what I call data augmentations using CV2, but thankfully PyTorch already includes some of these augmentations in a very seamless manner to integrate it into your code. So let me pull up another notebook. Okay, I'll share the link on Slack again under the same thread. Let me know if you can access that. you should be able to see something like this. Can you do it? Okay. Yeah, so instead of if you want to build a PyTorch model, which you'll probably be using. Yeah, so most of the stuff you can do from CV2, you can, well, from OpenCV, you can also do with PyTorch directly. So again, we'll be using matplotlib. And we didn't talk about it too much, but we were using Pillow from, which is native in Python, which is what you see here with PIL. So that's also provides some very basic utilities like loading images and stuff. Okay, and we'll be using, so this all just downloads this image from Disney's animated movie Frozen. So what you can do from Torch Vision is you can just, so Torch Vision is a separate package, but it's also built by the PyTorch team. So you can access various transformations by importing torchvision.transforms. And PyTorch provides several utilities here. So first of all, you see that we're using .compose. And what .compose does is simply that it takes various transformations and composes them into a single transformation. So with a single call, you do all the transformations. And here you can see the transformations that we're talking about earlier, like resizing, center crop, just is not a random crop, but rather it takes from the center of the image however many pixels you define. To tensor transforms it from whatever its original format is. It can be NumPy, it can be an image from Pillow, it can be whatever. So whatever this can handle, it takes it and transforms it into a PyTorch tensor, which we saw last time how to handle. Then we're doing normalization. So normalization is useful in machine learning in general because it can give, for example, your samples and zero average and unit standard deviation, which is easier to work with compared to whatever other distribution they may have. And then the final transformation again is you have gone to a tensor before and then you reproject to a Pillow image. So if you run this, this originally very large image is transformed to a 224 by 224 image with the normalization applied. Notice that for us humans, like when we're looking at the image, you can see significant changes, but for a computer, it doesn't really matter what the absolute numbers are. We really care about how these different colors relate to each other. And also here you're seeing some artifacts of the fact that we may have gone below 0 or above 225 in the pixel value. However, again, for a computer, that's no problem. But for our definition of how colors should be displayed on a screen, we go from 0 to 225, or we can also, when we're working in PyTorch, we usually just also reproject the 0 to 225 range to 0 to 1. because machine learning algorithms work better with smaller values, or you'll have to like kind of reinvent the whole machine learning stack to work with these larger integer values, which is not ideal. So we usually just project them to 0 to 1 and then further apply transformations like this normalization here. A note here is that you may see people doing normalizations with weird means and standard deviations that have been hard-coded into the code, and those are usually derived from the huge data set called ImageNet, which was collected almost 2 decades ago, so the first decade of the 21st century, by the end of it, and that's what enabled the deep learning revolution, as we're going to see next time. So moving on, again, we have the grayscale transformation, and it's wrapped in a composed object. But if you have a single transformation, you can just keep it on its own. So again, if you apply that, you get the grayscale image. Notice that you don't get any change in dimension, so you don't get the 224 by 224 image. And here we applied resizing, not to lose any information by, for example, just doing a very small crop right here. And that's, you usually lose some detail, but images are very much easier to work with when they have smaller dimensions, again, because these may contain like 10 million values. You want to decrease the size as much as possible while retaining the important information, so that your systems are basically more scalable, they're faster to run, etc. So I think this is zero padding, right? I mean, it's pretty much, that's already half the notebook. So
yeah, it's like zero padding. Fine.
Yeah, it's 5 pixels on the side, so zero padded. So why you want to do this is when we're applying those convolution kernels that we talked about earlier, where we go through the entire image and start applying the convolution to perform the transformation. I guess, can you link me to the whatever website you were using for the display of the kernels? So when you want to apply the kernels, you actually have to have data points for the kernels to be applied to. So if you try to apply them at the corner of the image, you are most usually gonna lose the edges of your image if you don't perform this zero padding. And the reason is because but I think I just just need to open it in this browser. So as you may see here, the actual element that's the result of applying this kernel to the image is not the one on the edge, is the one that's in the middle of the kernel. So zero padding is important, for example, to be able to apply the kernel like so. So you can see that not the whole kernel sits on the image. And in order to achieve that, there are various techniques. One of those is to zero pad. So to add zeros around the frame to be able to apply this kernel seamlessly to your image. Other techniques are you can do reflection of the image at the edges, so you actually have real values to perform the convolution with. So that is kind of like a hyperparameter, but I don't know how much it's like worth exploring, but it's something to keep in mind that if you do not zero pad, you are gonna decrease the dimension of your like images. So for the Gaussian blur, that's just another convolutional kernel. Yes, we can increase the hyperparameter here, which is what? So we kind of talked about adding noise to the image. And again, that's because when you're adding imperceptible noise to the image, the semantics of the image don't change. So you have an image of a cat and you add very small variations in some pixels. The semantics still remain the same. It's still a cat, and you want the algorithm to be able to perceive that. And there are actually techniques called adversarial techniques, where they go and like add very small noise to images and then change the label and train, and neural networks kind of train the noise basically to be able to change the label of the actual image. So if you've ever seen adversarial attacks where they take an image of a van, they add very small, imperceptible noise to humans, but because they have fine-tuned it to the model, it's able to change like the prediction from a van to, I don't know, selfies or something like that. So adding small, like using different techniques to add small noise to your models may be beneficial in that regard. And again, we're talking about different cameras, they may have different artifacts. So making your models robust to small noise perturbations is usually very useful. So again, I spoke earlier about cropping and we had to do it manually, but there are utilities in PyTorch, or rather Torch Vision, which give you multiple crops per image automatically. So you can see when we are applying this 5-crop transformation, we're taking the initially very large image and applying cropping to the 4 edges and then the center. And you can actually see that, I don't know, if we initially had, we were building a classifier to find which Disney movie this image came from. You can see that we only retained the semantics essentially on the first image, but for all the others, we're losing the main character. So what you can do is again do dot resize, so resize, say to some larger original dimension than compared to your crops, because the crops are 250 to 2 by 250. So let's do, I don't know, 284, and then let's reapply this, and you can see that for these crops, these are essentially different views of the same image. Again, the pixel values themselves are very different in these different crops, but hopefully the semantics are relatively the same. And therefore, you have created extra data for your algorithm to use. Again, we have the rotation here. That's actually a random rotation. So I think this defines the maximum angle you want to rotate your image with, and you can apply that. Again, if this was, if we were talking about digits here, perhaps we would want only very small rotations, because if you rotate a digit or a letter too much, then it may lose its semantics. And similarly to random rotation, we also have just random crops. So you can just run this multiple times and it's going to give you a different crop. Why you would use the 5 crops instead of using the random crops is that the 5 crops is just faster, and doing too much random perturbations to an image might not give you too much after some point where the algorithm has indeed learned that objects can appear in different points in the image and at different scales. And that would just be more computationally intensive, because every time you fetched an image to train the algorithm with, you would have to reapply the transformation over and over and over and over again, as opposed to applying it, say, once at the start of training and then just using the same transformation every time. And we have the horizontal flip. The hyperparameter here is the probability that you will apply the horizontal flip. So you see random horizontal flip with what we're building. So let's run it a couple of times. Yeah, we got both cases with 2 runs. And again, random rotation. I think that, yeah, this is specifically rotation. The previous one was affine transformation. I guess it's not, yeah, it's not actually. Yeah. So if you you obviously know what linear functions are, but you know what affine functions are? What do they mean? What does it mean to have if you have an affine function, what do you have of like, say, one-dimensional variable of x? So what would the linear function of x be? Come on, guys. It's gonna be a times x, where a is like a real number. And a affine transformation of x would be a times x plus b, where b is also a real number. So a times x plus b is not actually linear. People may call it linear, and it's kind of, it may be understood that it may also mean that you add a bias, what we call in machine learning, or you add a constant. So for the affine transformation, the constant is going to be the deviation. So it's going to be where you move the image, and the alpha in that case is going to be a matrix, and it's going to be a unitary matrix. How are they? I think, yeah, it's going to be a matrix. You're dialing something there. It's going to be a matrix that I think matrix times matrix transpose is going to be equal to the unit matrix. So where you have a unit in the diagonal and zeros everywhere else, which this defines a rotation for the image. So it's going to apply first in translation. So it's going to apply the constant of the affine transformation, and then it's going to apply the rotation, which is the multiplicative factor, which in the one-dimensional case was going to be your A. And yeah, we have again inversion, solarization, whatever that is. So you can see that these are very severe transformations. So if for the setting, for your setting, they change the semantics, then do not use them. I would argue for this one that perhaps it is changing the semantics of what we're seeing for the task of identifying which Disney movie this comes from, for example. So you may say that this is an invalid transformation for my problem, so I'm not going to use it. Same for solarization. And again, as we talked about with compose, you can apply all these kind of random transformations. So let's run it a bunch of times. You can see it's still frozen, it's still frozen, it's still frozen. Maybe you do not want to do like a vertical flip, but maybe a horizontal flip is fine. Depends on, again, your problem. You need to be aware of what your data looks like. You need to have a sense of what your data set is, so you know how you can augment it. And I guess here is an actual example. So we are gonna see the CIFAR-10 dataset. This is a dataset that contains images of animals. It's a very small data set. So it's what we would now call a toy data set. It only has 10 different categories. So that's where the 10 comes from. There is also the CIFAR 100, which has 100 categories. And people usually use that to benchmark very novel new ideas. But otherwise, it's not too useful to the research community, but it's useful for demonstration purposes, I guess. So here you can see we're doing the same thing I also did with MNIST for my workshop last week, where we're using the datasets module, which comes from, again, the same packets as the transformations came from, Torch Vision. So we're just gonna load CFAR 10 from Torch Vision. We are creating this transformation where, again, we're applying a random horizontal flip. Whatever animal is in the image, if you apply a horizontal flip, it doesn't change what that animal is, right? Random rotation, again, we're keeping the angle very small, because if you see, I don't know, a lion upside down, you wouldn't expect that to be in your data. So you perhaps don't want to model like very large rotations. Then we are transforming to tensor, and because machine learning models in PyTorch are going to use PyTorch tensors, and that's the format you want your data to be in. And then we're applying a normalization. So again, the normalization is just kind of a very generic, hard-coded basic one. But if you're gonna use a, say, pre-trained neural network, like a neural network that has been pre-trained on ImageNet, then you are gonna want to use the same transformation that was applied during the pre-training of the neural net, during when you are fine-tuning it to your specific test case, use case. So you have basically the same distribution in the data, because it's very difficult for neural networks to adjust to differences in data, to differences in distributions of the data. It's actually a very much open research direction, trying to cater models to different distributions. So let's not get too much into the details. I guess you can see here the categories. It also has airplanes and I guess automobiles. And here you can see a batch of data with the applied random transformations. As I said, this is a very much a toy data set, so the images are rather small. So you shouldn't expect to see that in actual data sets, or if you want to work with an actual data set, preferably it shouldn't be that low resolution. But yeah, I guess that's more akin to an actual use case for you guys, how you load the data set and how you perform these data augmentations if you wish to in PyTorch. So you can use this example when you're setting up your scripts, and we're probably going to use similar examples in our workshop next week when we delve into actually using neural networks, pre-trained neural networks, to perform different tasks. So I guess that was it for this week, right? Yeah. So let's stop sharing, and perhaps we can take some questions if you guys have, or I don't know if you are mentioning pre-trained neural nets. I don't know if you guys know what pre-training means or why it's useful, for example. I don't know if you have any questions about the transformations themselves. If you have any ideas for what projects you might want to pursue, we can start discussing now. Okay, so when you are initializing neural nets, there are two ways you can do that. The vanilla initialization, I guess, is just using random parameter initialization. So when you do not know anything about your task, you are just initializing with random, the parameters in the network are random with very small variance around 0, because as I said earlier, you want to keep your parameters small. And because your parameters are small, you also want your inputs to be small, which is why we go from 0 to 225 to 0 to 1, and then we further renormalize to make it zero mean and maybe unit variance. The other way you can initialize a neural network is basically initialize it randomly, train it on a related task, so the network starts to learn the semantics. So for CFAR 10 here, for example, you have images of whatever, airplanes, automobiles, birds, cats, deers, and stuff. You may be able to find another data set which is hopefully much larger than your data set is. For example, ImageNet. ImageNet has millions of images. This data set has tens of thousands at best. So you train your randomly initialized neural network on another task that's similar to yours. So you expect your neural network to learn some knowledge for the task that's going to be related to what you want to do. And then you take this pre-trained neural net on the other task and bring it to your task to do a little bit of training to cater it to your specific use case, but not randomly initialized. If you are using a randomly initialized neural network for your task, then you better have enough data to actually train it from scratch, or use a very small neural network so it has a very small number of parameters, which is going to be less powerful than these like very huge neural networks that like Meta and Google and all these people are training on maybe billions of images. Like for me as an academic researcher, for example, or you guys that you're going to do this project for the purposes of this workshop, you're not going to have access to billions of images for your task. And even if you did, you're not going to have access to resources, to GPUs, to like computational power to actually train on all those billions of images. So what you would do is look on the internet or these like libraries. So Torch Vision has pre-trained models. So you're going to look for trained parameters online, download them, use the model that the pre-trained parameters were actually used for, and then just fine-tune it with the few data that you have to perform the task that you want. And sometimes people like, it has been observed that when you're training a neural network on image data, like the first few layers learn very low-level features, like looking for edges, looking for angles, stuff like that. If you move on to higher layers, then you may be looking for shapes. And when you reach like the final layers of your very deep neural net, then you may have what we can call maybe templates of faces, or faces like human faces, templates of tigers, templates of, you know, these high level constructs, which are not directly like observable from individual pixels. So when people are doing the fine tuning, you usually want to retain the capabilities of having like these edge detectors and these shapes and all that kind of stuff. And you only want to like modify the very, very top of the stack where it has the specific concepts that you care about. And you may not want to have any tiger capability, say in your neural net. You may want to have just, I don't know, horses or whatever. So you modify only these top layers with a few data that you have, and you use essentially mostly the pre-trained and downloaded parameters and a few of the parameters you have trained to do the task. I don't know if that answers the question or if it created more. Okay, yeah. And by the way, like the ImageNet is a data set that has 1,000 categories, but it's stuff like this. It's trains, it's animals, it's objects like scissors and stuff. And people have taken models that have been pre-trained on ImageNet and used them to do medical imaging, for example, where you're looking at scans of chests and stuff to identify cancerous, whatever, this and that. So that tells you that the very low-level capabilities of edge detection are really transferable to whatever vision task you want. So We'll see next workshop how we can use pre-trained models, and you guys are definitely going to want to use them in your projects as well. Other questions about the projects? Have you guys started talking amongst yourselves to create teams, or are you planning on, because we can, I guess, since we know who's going to be in the computer vision track, we can just, instead of having individuals as teams, we can maybe create 2 or 3 groups based on common interests for you guys to be able to work with each other instead of doing it on your own, because it's going to be a daunting task to build like some machine learning applications on your own in like 3 weeks maybe. So keep that in mind. Maybe we're talking about with Kathy about creating specific channels for each track, and there you have the ability to speak with other like-minded individuals, I guess, and have direct access to the mentors of your specific track instead of everyone else. So you can discuss on what you want to do. Next week, we're also planning on including several links in, well, not next week it's spring break. The week after that, yeah, on the 24th, where we are going to include a bunch of links to project pages from like recent research projects. So when people in computer vision, when they publish papers, they usually come with links to web pages, because when you're doing, say, video processing or action recognition from video or robotic tasks and that kind of stuff, obviously you cannot really put that in your paper reports. So people use websites where they have embedded videos and all that kind of stuff. So I think that's going to be a very good resource for you to be able to think about what project you want to do. And researchers also tend to open source their models in the sense that they upload also their parameters. So when you find the project page, it's very likely that you'll also find a pre-trained neural network to do the task. So that's going to be very useful for you in building your project. So thinking of it, I think I'm just going to share with you guys every link I get as soon as I compile enough of them, and we don't have to wait until the next workshop, so you guys can start browsing these projects to get ideas for your own. But unless you have more questions, I think we can just
do one last show them the network diagram that they get an idea of what it actually does.
Do you want to
TensorFlow? I don't want to use a laptop. TensorFlow diagram. Yeah, the first one. So relating back to what he said about. Share your screen. Yeah, so relating back to what George said about using pre-trained models, right? So this is what a neural network actually looks like. So when
very small one.
Yeah, it's a very shallow neural network. And then when we add layers, that's when it becomes deeper and deeper. So that's what he was talking about, having a deep neural network, where in the first few layers, it's only going to detect, like, as he said, like just the edges and like the basic features from the images. And then as you go deeper, it's going to learn like more higher level features. And then what we were talking about being like parameters that you can import directly. So, like training just this neural network, like running it once, like so that they understand like what the parameters actually are. So when we discuss linear regression, right, we discussed calculating the coefficients. So when we are training a neural network, the outputs are parameters, and like getting these parameters through backpropagation, it's going to take a lot of time to have a huge data set. So you don't want to actually run this on your laptop, because it's never going to complete, or it's never going to output actually useful parameters. So what what we usually do is we take parameters that have already been calculated, and then we apply that to our task. So this is a very small example where you can see like even with these so many layers, it's not actually calculating it very well. You can see like the test losses, it's like just going on constant, and it's not going to improve any further. So like this, like training the neural network, adding layers, subtracting layers is an art in itself. Actually, like speaking like very like plainly, even this is a like a huge area of research. Is like what is actually happening inside the neural network is not apparent to even like computer scientists. So we use that. We Most of this is going to be like trial and error, like adding and subtracting layers, adding neurons in each layer, and then you figure out like this was an actual assignment for one of my courses, like just like adding layers and subtracting layers. They gave us this and they were like you just figure out like what works and what doesn't. There's no like logic to this. So what we usually do is just like use pre-trained models so that we don't have to go through the process of like figuring out the parameters ourselves.
But you can see like the space here, how the output space is shaped. So when you're seeing this blue background, it's the points in the 2D space that the classifier assigns to the blue category and the orange for the orange category. So you can see how different it is from just a linear classifier where it would be just a line. And you can see that it can capture like intricate structures. So your data, let me stop sharing because my computer is complaining. So you can see that for this kind of even intricate structure of the data, this like the shape of the space that the model learns starts to kind of capture that structure. And you can see here, I guess, they are visualizing right here what templates these neurons are looking for. And you can see that in the beginning, it's like pretty simple. Like you have this, I don't know, this looking for circles or looking for right here, for example, looking for this triangle at the edge. But as you move through the neural network, you get more intricate structures. So what basically they're doing is they're taking kind of like a weighted average of all the previous templates that the model has built in its earlier layers and combining them to create more intricate templates. So I can also take you for a more complex visualization to the resource I suggested in my workshop last week. I hope it's here. I don't actually remember where the figure is, but something is here, I guess. So conceptually, it's kind of stuff like this, where you start with edge detection, and then you move to, I don't know, eyes and ears and faces, and then you actually go to more complete stuff like wheels of cars, caricatures of a person. I don't know what that is. And the deeper the neural network, the more concepts you're going to be building on top of your existing concepts as well. But then it becomes difficult to train it because it's more computationally intensive. And to make the networks really deep, there are quite a few tricks that people have come up with to actually pass the information sufficiently back into the neural net. Yeah, I'm not seeing it here. Maybe here. Okay, I may be misremembering the figure. That maybe, yeah, it may be from some other research, but I guess what we saw was good enough so far. So I guess now we can wrap up this week's workshop, and next week again, next workshop is going to be in 2 weeks, but on Friday again at our like regular time. we're gonna look into pre-trained neural nets, how you can use them, how you can access them, what kind of tools you have, what kind of information they provide to you with respect to your data. And I would say, like for this week, knowledge of what we presented last week was not mandatory, but if you are gonna start using neural networks to process your data, then you're gonna need to know how to handle tensors, what the different dimensions represent, what the network expects, how to set up a neural network, how to set up a training routine. Most of the stuff, if you do the very basic stuff, is pretty easy to get a hang of. And then furthermore, you can leverage existing libraries to do more complicated stuff during training. And we're gonna try to show you as much as possible on the 24th. And then the 31st, we're gonna look into any leftovers from the workshops, the workshop on the 21st that we may have. I think we're gonna have Dr. Lowe speak to us, which is our Google mentor. And then we'll move on to discussion about your projects, because they're gonna be 2 weeks after that workshop, the presentations. So you should start thinking right now about your projects, because you have like 5 weeks, I think. Yeah, you have a month to, yeah, a month, 4 to 5 weeks to complete the projects for the workshop. So start thinking, don't think in terms of neural networks, think in terms of something interesting you want implemented, some automation you want to apply in something that like it's nagging you, I don't know, something you would wish to automate in computer that requires vision, that it's of immediate use to you, or I don't know, some greater purpose, whatever, something. Just think in terms of applications and don't think in terms of neural networks. And if you have the applications, then we'll figure out how to build those from existing resources.
Any questions? Yeah, it's gonna be in a group. We're not sure like how many will be in a group right now. Most probably it's gonna be 2 or 3 people per group. Because doing it individually in that amount